Good morning. This is already October 23rd. About a month from now will be Thanksgiving. I don't really want to think that far ahead. There's a lot to happen in this class. Today, for those of you that choose to watch the video, and if you're watching the video from outside, we're giving an exam today, or I'm giving an exam, so the lecture will be much shorter today, but then we'll resume again next week with the full time. So to get going, we're going to jump back into the multi-rate sampling that we talked through last time. Before I actually do that, and before the time starts to escape me, I just want to point out that coming up is going to be this first project. And I've been working on it, but I haven't reposted it yet. So let's just take a quick look at what I did. Because of the way the website here was created at the end of the summer, all the dates got mangled up. So Project 1 and Project 2 show that they're dates from 2024, but they're not. They're the dates when the site was recreated. So they're going to be rebuilt. But just to take a brief look at this, this is what the project will look like. Very little is going to change in it. This upper section I've already re-edited. It's got the new dates in it. And it's going to be due during Thanksgiving week. I think the only thing I've changed there is I hope to get you to get it turned in by Wednesday, if you can do that. And we'll negotiate on stuff as time goes along. In terms of what the project tasks are, the main task that's going to change slightly is this polyphase decimation filter that was done in Python and then compared to Julia using a pre-built component that's in the Julia DSP package. I'm not going to go that route. Instead, what I'm planning on, but haven't tested it out yet, is that SciPy.signal has a package for polyphase filtering all wrapped up in a component as well. So I'm thinking of doing that as the comparison. You will write one, and we'll be talking about that probably not quite today, but next week, what a polyphase filter looks like. And then you will compare it. You will do timing. The main thing that problem will accomplish, though, is timing, learning how to just time code using TimeIt, which is part of Jupyter, actually. It's a neat little function. It's not unlike what MATLAB has too, but timing code is something that I was doing at least one of the problems. It was in C++, which was a lot more fun a few years back because C++ has got a lot of libraries and things that are in the standard library. But I'm not going to go down that path either. So you can breathe a sigh of relief. I mean, installing other tools like C++ and the compilers, I'll maybe talk about that some other day. And in a little bit, we'll change down in here. PyAudio helper _old will be in the package. This sound device and sound device helper was something I considered. It's another package out there, but we don't need to go that way because we've already explored PyAudio helper and we know that that works. So I'll announce this when it does change. I may even be working on it while you're taking the exam later this morning. So back over to the notes. One of the things I want to do with the multi-rate, and we were looking at decimation in particular, remember this equation here for the spectrum of an analog signal when the sampling period is t. Then we looked at when we effectively downsample after we've created the discrete time waveform, but we can still relate it back to the spectrum in the analog signal by putting mt underneath here. And I was getting confused when I was talking about how fast or how slow the spectrum rolls out with omega. So what I meant to say, rather than faster, because that's going to come up in the upsampling, because m is in the denominator, it takes a larger value of omega to go across the omega axis to get the same net effect. So I drew a little picture just a few minutes ago in here, just to try to emphasize that. And this is like the spectral axis omega, and if I had a spectral shape, it's a really wavy line. My hands were really cold, and I are still a little bit chilled from riding my bike, so I felt like it's a little bit chilled. So it looks wiggly, not on purpose, but just the way my hand was working. At any rate, if it's just omega and we're going down a slope, and the intercept, I'm not writing the equation for the line, but suppose its intercept is at omega c, that would be with m is equal to 1, and if m is equal to 2, in other words, if we were comparing that to omega over m, it's going to stretch out to twice as much travel distance on the omega axis. That's what I was trying to say last week, and this will hold true in the examples we're going to be looking at. The opposite of this is going to hold true with the upsampler. It's going to be m times omega, and that's going to have a sort of a totally different effect. And these things, to me, are so vivid because what am I doing and what I'm working on? I'm doing this multi-rate stuff, too. I was using a linear interpolator to effectively change the sample rate, and I'm sort of modeling FPGA-type components because of where I'm at with my interfacing with what I call the implementers. I mean, I'm the systems architect person on this particular aspect of a project, and I have these FPGA people that are working alongside me. They don't know much about signal processing. They do know a lot about writing. In this case, VHDL, I think, is what they're going to be writing in. And I experienced this over so many years of my career, and I've always thought people should be good at both if they're going to do this. But guess what? It just hasn't changed that much. I would still say, though, that if you take advanced digital design, or I've taken it, or taking it concurrently, I believe Dr. Pereira teaches it in the fall, it's a good thing to have, even if you're a systems person. And if you never do this again, but are going to do FPGA development, this background is still probably going to come and be in your face at some point. So there's sort of a dividing line there, though, still. And in the team that I'm on, that's how it's kind of divided. And so I hand off a design that goes over to the implementers, and then they start implementing it, they start testing it, they generate waveforms, they eventually have it running in the hardware, then there'll be, testing in the lab and stuff like that. So that's just sort of what I've been up to the last few days. So the one problem, example problem that we started on last week was an m is equal to 2, and we had the triangular shaped spectrum. It's just a convenient model. It's not a practical spectrum, but it's just a convenient model to talk about for a spectrum, and I'm going to show you that in the Jupyter Notebook here shortly as well. So we took a particular case where I'm drawing it in the discrete time frequency axis, little omega, and I'm saying that this omega n, in this case, is pi over 2, and then when m is equal to 2, besides getting the amplitude factor, the scaling factor 1 over mt, we see that this pi over 2 stretches out to pi, just like I showed you with the picture, because of the downsampling stretches things out longer. When we upsample, it's going to pack things together tighter. So in this case, this works just fine because it was premeditated that this cutoff would be pi over 2, and when we decimated or downsampled by 2, it would just hit pi, and that means we're not aliasing. We're working, we're working tight with the spectrum overlap. It's just 0 right at this point. So the next example is to go ahead and increase m, and increase m without changing the spectrum in this current example. So this next bullet down here just says that typically you'll have to filter the input signal with an ideal low-pass filter or some low-pass filter to avoid aliasing, and the value that has to be needs to be pi over m, and that's just to poke that in your brain. If you decimate or downsample by m, you need to be band limited to pi over m. And we'll see how that works out in an example here. So this is what the pre-filter would look like, a low-pass filter, cutoff frequency, and for whatever reason, there's a slash that's missing, a rendering problem, I guess, again, and then downsampled by m. So in this example, we see what happens if we downsample by m is equal to 3. So now the pi over 2 that you see up there stretches out to where? I mean, this is a good test. Are you following my directions or following my thinking? It's going to move out to 3 times pi over 2. So it's going to hit right out here. When you work the homework, you're going to be drawing sketches of this. And it's going to be required, actually, that you have sketches kind of like this when you eventually do your second exam, too. But the homework problems, I generally recommend having a stack of plots where you start at the beginning, before sampling, and then sample it, and then show decimation and stretching and scaling and all those other good things. So what do we do about that? The pre-filter sitting out in front of that, if it were to cut off at pi over 2, it wouldn't matter, or pi over 3, I mean, because we're m is equal to 3 in this case. So we need to make sure the cutoff frequency of the signal before it goes into the downsampler is at pi over 3 in the omega axis. So that's this guy right here. And so I would draw a stack of plots now. The first is the original signal with cutoff at pi over 3. And actually, I'm looking at that. I need to have it at pi over 3. So that's my anti-aliasing filter, or my pre-filter. So the spectrum now, there could have been another plot above this of the original signal. I didn't show that on here, but if I was thinking ahead to how you'd be doing this on the exam or on a homework problem, you would start by drawing the spectrum. Something like this, and you'd be acknowledging the fact that that was originally pi over 2 in the original spectrum, and that is not narrow enough bandwidth to go through the downsampling by 3 without any aliasing. So then the next step below that would be, say, to show that there's a filter that's going to come along and it's going to create the house spectrum that I talked about last week. It makes a little, looks like the side profile of a house. It clips off some of the higher frequencies, and then when we downsample by 3, it perfectly meshes together because the pi over 3 is, keep forgetting with the microphone, I can walk around a bit. Pi over 3 stretches out to exactly pi. So it's like a perfect fit to do that. And of course, there's a scaling factor in there too, when we downsample of 1 over 3 times t, effectively. Does that stuff make sense? You can do that. How can we actually draw pictures? I'm noticing in grading homework, a lot of you aren't exploring Python like I would hope. I don't think anybody in the homework tried the partial fraction expansions in Python to check their work, and there were a lot of mistakes for some people, getting the coefficients wrong. I'm not going to dwell on that. You're taking the exam. I don't want to discourage you because the exam problems aren't going to be that complicated. You'll be able to just work it out without using Python. What I want to do, though, before we jump over and look at upsampling, just look at how I can synthesize this. So the way I synthesize something to play around with it in Python, I use this transform pair right here. The pen is working today. At any rate, I'm using sine omega c n over pi n, and that corresponds to a spectrum that's band limited to omega C. But that's a rectangular shaped spectrum, and holding with tradition of the book and most other people that write about sampling and multi-rate sampling, the triangle shaped spectrum is just more conventional. So how can I do that? Well, I write about that right here. Get the right tab and move over. By the way, since I'm hung up on this, when I'm opening and closing notebooks, the second tab down on Jupyter has two tabs in it. It has open tabs. I only have one notebook open, and then it will list kernels that happen to be running. And because I have Julia running on here, I close that notebook, but this is a really excellent example to bring up. Notice that there's a kernel running still for Julia. I had this thing called Quick Test that I ran a week or so ago, and I shut the notebook down so you don't see it up here, but the kernel is still running, and it's consuming some resources. So what should I do? I should kill it, right? That's what I do. I'll just go in and say, shut it down, I don't need it anymore. And if it takes something else with it down that I want, I'll be frustrated. But I also can see there's a Chapter 3 notebook kernel that is still running. I never shut that down either, apparently. So I'm going to get rid of that too. So that's a nice little tab, and of course the one beneath it is our table of contents, which I was kind of heading for. And I'll move that out of the way. So this is just a restatement of the Fourier transform pair for the sinc function. And then I'm just saying if I square the sinc function in the time domain side, that will result in a convolution on the frequency domain side. We actually called it periodic convolution, but it will be the convolution of a rectangle with a rectangle, which all electrical engineers should have in their memory bank. What is that shape? It's a triangle, right? So it'll be perfectly a triangle, but the thing about when you convolve a rectangle that's, say, this wide with another rectangle, the base is a triangle that's twice as wide. That's like bread and butter. I mean, you just know that that's true, and you think that way in a lot of different applications where you think, oh, the spectrum's going to get broadened because I'm doing like a squaring operation. So that's how I generated this. The detailed math of connecting this sinc function with that, and then why did I put 25 down here? I didn't really have a time to put it on paper. I had this in my notebook, and then I said, oh, I should explain that. I didn't have enough time. I'll probably add that to this notebook. But at any rate, I'm creating a sinc function in here, and I'm putting 25 in there, and that's going to produce a waveform that looks like that. And then to get its frequency response, I'm just going to use freq z like we talked about weeks ago, put the signal in for the B coefficients in freq z and just put 1 in for the A, and then I'm going to sweep it, and I'm going to sweep it in frequency, the normalized digital frequency, omega over 2 pi, and I'm going to sweep it from minus 1.5 to plus 1.5, and so effectively I've got the same thing that I just had in the notes. I've got a nice triangle shape. It's repeating because of the periodicity, and that's the way freq z manages it all for us. That's the way it works. And this is 0.25, which is pi over 2 in the omega domain. So then I come along down here and I say, let's downsample it, and I'm going to downsample it using the downsample function that I have in this signal sig-sis module. I'm pretty sure it's in SciPy somewhere. I just rewrote it when I wrote that dummies book. I wanted it to be easy to find. So I'm downsampling x, and remember from last week there's an optional parameter to change the phase of the samples, but I'm just using it at its default. Downsample by 2, and then I'm also going to create an axis that corresponds to the time axis. If I wanted to plot the waveform, then I'd have to do some scaling on that if I wanted to. but I'm mostly interested in just looking at the spectrum. So there's the spectrum. The time domain is up above. It's not really clear to see that it's a sync squared because the amplitudes are so low, but the most important thing is that. And if I was to change this to a bigger number, then it's going to be a higher frequency. So suppose I make that, what do I want to make it? What would you like me to make it? I guess I should go up here. This would be more convincing to start up here. If you're not wanting to do the math and just want to be hacking your way through, which is okay at times, just let me get something going. If I put in 50 in here and run it, oops. And then I go ahead, so it's fatter, so it should be a narrower spectrum. Sure enough, it is. So it moved from being at 0.25 to 0.125 is what I believe it's at. So if I wanted to change it, so I've just established what a rule of thumb would be. So if I want it to be set up for pi over 3, what should I do? I was at 25, and that just fit, so I should change it to 16.66. Let's just see what that does. So I think this is going to work right, or it's not going to work right, I mean, but it's now modeling, well, let's just go ahead and take a look at it. It's bigger than 0.25. As a matter of fact, it's pretty much already on top of 0.5. So if I put that into my downsample by 2 over here, oops. Sometimes in my notebooks you'll see an extra period in there. If you don't know Python's history well enough, you might say, why did I put periods there? Well, that in Python changes it between an integer and a float if I put a period behind it. In the earlier version 2 of Python that I started, that's how I learned, was with Python 2. When you did a division of, say, 5 by 16 as 2 integers, it would give you an integer. It would automatically truncate it and be the nearest integer, which would have been 0 in that case. So then in Python 3, they added a notation where if you just used ordinary division of 2 integers, it gives you a float. If you use 2 slashes, it gives you an integer again. So they changed the model a little bit. So you might see in some code where they've got 2 slashes, and that's what they're doing with that. Case in point, 5 over 16 is that. Put 2 slashes in there, and it's 0 because it's doing integer division, and it's a number that's less than 1/2. And if I was to change this to 8, still 0, but if I was to make it 8.1, still 0. I guess I have to go all the way up to 16. Yeah, there we go. It took me a while to get used to that, and my code library was already published at that point, so me and the co-author, we had to rework stuff because it changed some things. We had to make it backwards compatible is what we did initially, which was even more work to make it work for the two different forms. Okay, so run that again. Okay, now I'm still downsampling by 2, and what did I do here? I put in 16.66, downsampled by 2, and we're not aliasing. Let's put in 3 though, downsampled by 3, and Now what's it complaining about? Now I had a time axis thing and I have an integer error right now, I guess. Obviously I didn't practice at this. I've got something with the error. Yeah, there's my problem. Let me just not do that. When I downsampled the axes and then divided it by 2, it was no longer an integer. So I just committed the error that I was talking about. What I'm going to do is just take that away from there. I thought that would have solved it. Oh, I know what I did wrong. I didn't put 3 in there. That's what I was doing wrong. So now they're just touching together. So I've accomplished that goal. I don't have a filter in here that I can slap in there to show that I can avoid aliasing, but they're touching together now, whereas they weren't before. This is a little bit of a, you got to be careful what you're doing because it's not a perfect triangle, and when they blend together, it won't always look like a sharp edge. You're seeing it's kind of rounded looking right now, so actually they are overlapping, I believe, in theory. Why do I say that? It's because in this picture right here, when I use the 16.667, if this was at 1/4, and now I'm going to stretch over by 3, it should be over here at 3/4. Well, this is already greater than 1/4, so it's now stretching out to be way up over here somewhere. This value is going to stretch up to 3 times this value, and it's going to put it way up in here. So now these two slopes are kind of blending together, and I think it is creating more of a parabola, I think. I don't really want to get too hung up on that. Just want to go back over to the next part, and that is increasing the sampling rate by a factor of L, the upsampling factor. So this is the opposite of the downsampler. It's the upsampler, and with the upsampler, they call it X sub E is called the expansion. In the book, they call this expanding the signal. When they expand the signal, what they say is that it equals 0 unless it hits on an integer. So this is another case of integer understandings going on. The expanded signal will have the original input signal samples whenever n over L is an integer, and when n over L is not an integer, then it's just 0. And that's explained right here in the blue box, where it just says if n are these integers, and then plus and minus L, plus and minus 2L, and so on, that means this ratio is an integer, then we get the value of the sequence. But if it's not, then we get 0. So if you put that together using a delta sequence, you're just basically repeating the input samples, but now you're going to be putting L minus 1 zeros in between them. And we'll be able to look at that in a second here too. But in terms of Python, when I do go to look at it, the function names are the same. It's just upsample now by some factor. Oops, over here. No. So when we look at that in the frequency domain, the expanded signal that has the 0 stuffed in between, Fourier transform that on both sides, we get the expanded signal spectrum. And this one is far cleaner to analyze than the downsampler, because we don't have to worry about the images overlapping each other with that extra term summation that was left over at the end. So now we just simply use that inside the sum, and it just reduces the terms that we're summing over, and effectively it says omega now gets replaced by omega times L. So it looks like a Fourier transform with omega replaced by omega times L. And that's the expanded signal spectrum. But because it's in the numerator, if I was to go draw this picture that I was showing you over here, if I was to redraw that, if I was to rewrite that out, oops. My finger's not working very good. I keep trying to change the color and I miss it. And then what happens when you're making the omega axis roll out more rapidly because of the L in the numerator, the periodicity of the function now takes hold, so it's going to create an image at the next image, rather than occurring at 2 pi, is going to be occurring at 2 pi over L. So this whole thing is going to repeat again right there. Oops. I guess double tapping on the screen, which I didn't know I was doing, it zoomed in on it for me. At any rate, we'll see that in how the mathematics works. So it repeats it more often rather than multiples of 2 pi. It will be at 2 pi over L, so it will repeat over and over again. See, I'm impatient. You can tell. I hit, and then my mouse moved, and then I accidentally tried to close it down. So the best way to see this action is to go with drawing a picture again. So suppose we start off with a spectrum that's band limited to pi perfectly, and then if we increase the sampling rate by a factor of L is equal to 2, this is supposed to be it's going to hit pi over L, but then there's going to be an immediate image starting centered on pi, because that's 2 pi over 2, which is pi. So we'll have another repeat there, and that's at the top of the page right now, the way I've got it shown. And then, of course, it comes back again at 2 pi as well. But what the interpolation filter does, and I didn't mention that explicitly up here, is that what you have to follow an upsampler with it is an interpolator, because the zeros that are stuffed in between are what are responsible for making replications of the original spectrum, only compressed, and then the interpolator smooths all that out, just like interpolation would work that you learned about a long time ago. If you have 2 points and you want to interpolate points in between, you have a function to create those points, and that's what the low-pass filter is doing for you. It's interpolating. So here we have that picture, expansion by 2, and then the interpolating filter, which is a band-limiting filter that cuts off at now pi over L, whereas before we were doing pi over M for the downsampler, and that gets rid of the images. So now we're effectively, if we're doing an ideal interpolator, it would be a sinc function again, and it would perfectly eliminate all those spectral images. Just yesterday I was using an approximation, an interpolation operation, and the images do show up. They're just not squashed down far enough, and that's kind of the standard thing when you're doing this in practice. Is the ideal low-pass filter removes those images perfectly, but a real interpolation filter will only suppress them by so many dB down relative to the signal of interest. So that's what I talk about here. You get a good approximation. And a simple idea of how to interpolate is this idea right here. Let the impulse response of the filter be a triangle shape. And this is a finite impulse response filter. I haven't shifted it to make it causal. It's just the concept is if I use a triangle shape and then go through this operation with that impulse response, this is now L is equal to 5. So if this was the original signal just had a bunch of samples rolling along in it, and I decided to create this triangle-shaped filter as my interpolation filter, upsampled by 5. You can see that there's L minus 1, 0 stuffed in between every sample. That's the expander idea. And then the interpolation filter comes along and puts those X-topped samples in because it's linearly interpolating. And that's just making it kind of obvious as to how this interpolation operation works. Now, just right off the bat, we can see that if we choose this interpolation filter as a triangle, here we are at the sinc squared function. I should look in here. This is what I needed in Python. This is the exact expression for getting, or it's related to what I was doing. The sinc squared, again, is the triangle in the time domain. So what's interesting here is that the ideal low-pass filter, the ideal upsampling interpolation filter would say cutoff at pi over 5. Because that will remove any images from leaking in. Now there's going to be an image here. And so on, 2 pi over 5, 4 pi over 5, and so on. So the idea is that filter comes along and gets rid of the images that are going to start stacking up on either side. If we put this linear interpolator in, its frequency response is this sinc squared function, and it has this bad behavior in that it's going to let some of these images pop through because of the fact that it doesn't perfectly cut off. And it also takes away some of my signal spectrum. It causes something that's called frequency droop. In other words, it's rolling off before you get to the band edge, so it's removing some energy. So I think I've probably given you the homework problem that talks about how if you use something like this, what you can do is you can compensate the input signal spectrum by peaking up the edges of it above and below so that it can anticipate that the interpolation filter is going to roll it off a bit. Is that making sense? The idea of an equalizer in the frequency domain, trying to flatten the overall response. And let's just go look in Python now really quickly. So here I use the same sinc function model, or sinc squared model. So there's back to the spectrum I started with before, but now I'm going to upsample by a factor of, no matter how I set the mouse on this computer, it either jumps or it aggravates me. Either way, I can't find a good way to do it. So I'm going to set L equal to 2 in this example. I've already upsampled by 2. So I've got images that are occurring now at 0.5 and so on. So what happens if I set that to 3? I get the same axes issue that I did before. I got to change it at second time in here. I think. What does my error say way down here? Yep, 2 different sizes, so I broke it somewhere. I can't believe I never used this idea in class before, but it's been too long to remember. Just forget about that. So now you see you've got more images, and now just increase it to 4. And even more images. It just starts filling in. These should be ideal triangles if the spectrum is a triangle, but the idea is that you have to come along and knock out all of these images that are sitting in here with your linear interpolation filter. Fix my typing error. So here I came along and decided to design an equal ripple low-pass filter as an interpolation filter, and go back to the original problem. Since this is set up to be upsampling by 2, better change this back to 2. So the idea is this filter should come along. It's the low-pass interpolation filter designed to cut off over here at 0.25, and I'm going to apply this apply this filter to it, designed as an equal ripple filter. There's its frequency response. You see it's cutting off at just above 0.2, and it's going to drop down before just past 0.25. So you'll get to play around with some filter design, but what I did is I designed it to have a transition right over the 0.25 value, and that's what these numbers are doing here. And now it's clear because the filter has come along and knocked it down. But guess what? It's only clear if I look at it in a linear scale. If I was to put this in dB, we would see some leakage in there. We're not going to see very much, so how daring do I want to be on this? Maybe I don't want to try it. I was going to say I could take this spectrum and plot it. 20 times log 10, and that should be a decibel scale. There we go. Doesn't look like a triangle because I've logged it, but you can see that down about 70 dB, because that's the stop band I set filter. Actually, I set it at 80 dB down. This is the ripple in the stop band. But the idea is that you can see it is 80 dB because this is over 0 and that's at around 70. So this is what I was alluding to with the practical filter. It's still there, but it's knocked way down. Is that making sense? We want it to go totally away, but with real filters we can only do so much, so we knocked it down a lot. Okay, moving on. So now we're set up to say if we want to change the sampling rate by a rational number factor, then it's logical to organize our interpolator and decimator in this fashion where the filters are adjacent to each other. So we first would interpolate by L, upsample by L, and then downsample by M, and then choose the cutoff frequency to be the minimum value between pi over L and pi over M. And then we would be implementing a rate change. And an example that I talked a little bit about or vice versa. suppose in the studio you're recording at 48 kilosamples, and you're going to be formatting it to put on a compact disc that's designed for 44.1 kilosamples per second. So we want to implement a rate change where we upsample by a ratio, by an integer, and then downsample by another integer. So how could we do that here? And 480, so I would upsample by what number? If I want to affect a change of from 48 down to 44.1, I want to upsample by 441 and then downsample by 480, and then that's going to create a sampling rate of 44.1. Does the math look right? I'm just using sort of an intuitive feel that I want the rate to come out smaller than the input rate. So I have to be going down by the bigger of those two integers, 480, and I have to then go up by 441. That is hard to do because those are large integers. There's a lot of rate change going on there. So that's where polyphase comes in and some other factors show up. So how are some of these things utilized? I'm starting to get overheated. So back in the day when the compact disc player came out, the compact disc player often employed in the early days an upsampling operation by 2 or 4 to avoid or to create an easier reconstruction of the analog waveform. So when you're at 44.1 and you look at what happens when you're going to take it off the compact disc at 44.1, these are going to be all the spectral images that will naturally occur in the spectrum, the discrete time waveform at 44.1 kilohertz. So if the A to D converter, which we'll learn a little bit later, but you probably understand that an A to D converter or D to A converter generally has a sample and hold or zero order hold at its output. So it's going to hold the sample that it outputs now until the next new sample comes along, and then it will change values. So the effect of that is what's called a zero order hold or rectangular extension of the pulse in the time domain, so that in the frequency domain it's introducing this filtering operation of the sync function, and that's what I have shown shadowed in gray there. And then you still have to come along with an analog reconstruction filter and cut off at the half sampling rate to then get the output to your headphones. So there's droop involved, so there's inverse sync function correction filters that are built into some D to A's, but this is just not optimal because it's difficult to build that. So what they came along with an innovation was to upsample by 4 before the samples are output into the analog to digital filter. And that's what they've done here. For whatever reason, I think I'm going into a blackout. So I think I'm going to stop so I can sit down. Okay? I don't know why it's happening. It's like my blood pressure is dropping way too much. Either that or I'm getting really sick. So this was a great innovation back in the 70s. I'm going to stop. You guys can take your break early. I don't want to faint.